Hello and welcome. My name is Tom Webb. I am a postdoctoral researcher at the University of York studying the coastal cryosphere. Welcome to the Cryosphere Pavilion and this session on extreme weather, sea ice and Arctic warming. We are joined by hubs in Geneva and also in Stockholm. If you have any questions, feel free to ask it in the chat or at your hubs directed to the speaker in the question and answer session. So now let me welcome Walt Meyer to the stage. He is from the University of Colorado Boulder and also the National Snow and Ice Data Center. Thank you.
All right. Thank you for the introduction. So again, I'm going to talk a little bit. This will be a probably fairly short, a little bit about sea ice and the warming and some of the impacts on extremes that we see both within and potentially outside of the Arctic as well. So I'm at the National Snow and Ice Data Center, and we're at the University of Colorado. And just a quick little background for folks that are not familiar. We have a pretty sizable research group and do a lot of research in all kinds of aspects of the cryosphere, snow, sea ice, permafrost, glaciers, Greenland, Antarctica. But our main section is actually on data archive and distribution. We're one of the NASA data centers for the data center for snow and ice. So we archive all the NASA products. We also have a NOAA data center there as well, and house that. We also have some projects that support local and traditional knowledge. So that's also a component. We do research with communities and partner with communities in the Arctic, and do some outreach and public education as well. So in terms of the Arctic, for those that were at my previous presentation, I talked about the extremes that we're seeing in the Arctic. You're probably familiar with the real extreme sea ice loss that we've seen. That's one of the big changes in terms of the Arctic Ocean. There's much less ice cover year round, particularly during the summer season and into the autumn. And this is the October trend. You can see the significant trend in the blue shades there, about 12-13% per decade of losing ice, particularly on the Siberian side. And that it leads to more autumn warming. One of the biggest signals we see in the Arctic in terms of the climate is the warming in the autumn, because what happens is you have the ice-free ocean in October into November and even into December now. And the atmosphere, the sun has gone down, the atmosphere starts to cool, but you have this big heat source, and that heat is providing energy and providing heat to the Arctic and keeps the atmosphere warmer. So you see a lot of surface level, and even that heat even goes up higher into the atmosphere. So that autumn warming, that open water, it's more energy and more moisture. So potential for more storms and greater, more significant storms. There's also more open water. This is throughout the summer, even, and even you have earlier opening in the springtime. So you overall have more open water. It's a longer fetch area of open water where the winds can blow across. So that leads to larger waves. And the coastline, those can have big impacts, coastal flooding. And then as we're also seeing thawing and permafrost along the coastline and throughout the Arctic, that leads to coastal erosion. And as we're opening things up, there's also an impact in terms of open shipping lanes, and then the ocean effect, coastal snow, which I'll talk about in a couple minutes too, and rain on snow events. I'm not going to talk too much about that. There's a group at NSIDC where I'm at that has a project that is looking at this, led by my colleague, our director, Mark Serez. And these have a big impact as well, where you're getting warmer temperatures. You have more rain events instead of snow events. And that rain on snow has big impacts on the terrestrial, as well as potentially on the sea ice and ocean areas. So folks have probably seen this, the Arctic amplification. This is where the Arctic is warming 2 to 3 times faster than the rest of the globe. This is a really nice image. Zach Labe, who's at Colorado State University, he has a really nice website and puts together some really nice figures. So I often steal liberally from him because it saves me a lot of time. But this is a really nice figure. This is from NOAA in NASA GISS. Temperatures, and you see the Arctic is about a 3 degree C temperature increase compared to about 1 degree for the global average. And this is due to the loss of sea ice and the feedbacks that we see as the Arctic sea ice decreases. You've got the high albedo sea ice being replaced by the low albedo ocean. That means more heat gets absorbed. And again, a lot of this is happening in the autumn and into winter region. And this next shows that this is a little probably complicated, but this is another nice figure from Zach Labe, January through December on the y-axis from top to bottom, and then the years on the x-axis starting in 1950 actually. And this is basically the ranking of the individual years for each month. And basically the colder months, the lower ranked years are in blue, and then it converts into red for the warmest. So the darkest red is the warmest year of each month, and then the darkest blue is the coldest year. And what you see, obviously, all the reds over on the right side in their more recent years. So this is your warming, but you also see the red is focused on the autumn into winter, and to some degree into spring, March and April as well. Not so much in the summer. And that's because you have in the summertime, all the energy is going into melting the ice. So there's not as much of an anomaly in the temperature, even though you have a lot more energy going into the system. You're melting the ice, or you're warming the ocean, and the atmosphere stays pretty much the same. So it's less. There's still a warming trend, but it's much less notable than in the autumn and through spring. So stronger storms. One of the you have the ocean, and that provides a source for humidity, for moisture, and heat for storms. So when you have ice not present, that allows these storms that can develop and then penetrate farther into the ice pack and into the Arctic in general. And one of the most notable ones that we had was what we call the Great August Cyclone in 2012. That was a really strong low, below 980 millibar low, so very strong, and it tracked into the Arctic. And one of the things that was notable for at that time was what it did to the sea ice. It tracked in the top is this is University of Bremen sea ice, the concentration. Purple is the highest concentration. I left off a color scale there, but and you can see a bunch of ice in like the Beaufort, Chukchi, East Siberian Sea region there on August 4th. And less than a week later, 5 days later, most of that ice had disappeared. And that's where this cyclone churned across. And basically it brought heat. It churned the waves. It mixed up ocean heat, brought in atmospheric heat. The waves broke up the ice cover and really caused the ice to really the ice loss to really accelerate. So this was one factor in why the 2012 is our record low sea ice rate, and it still is. Because of that storm. Not the only reason. It was a really warm year, and we had a lot of ice melt anyway. But that was a big factor. And one of the things with that, it hit at the right place and at the right time. August is normally a period when things are starting to freeze up in the high north. You still are melting ice in the around the ice edge. That's mainly due to ocean heat. Actually, at that point, by the time you get to August, the sun is going down. But this was actually, we saw an acceleration in the ice loss in August. So that was really unusual. We haven't seen quite the same thing since then. And that's because we have had storms come through and some pretty strong ones, but they haven't tracked in the right place, in the right direction to cause the rapid ice loss. But what we do see happen is if these storms track over open water towards the coastline, then you have potential impacts. And again, it depends where they track and when. But there's been several cases of some pretty extreme coastal erosion with these northern communities along the coast. The most famous one is Shishmaref, Alaska. And it's gotten a lot of notice. You probably have heard about it because they actually have, they've started to lose buildings, roads have been washed away. It's right on the coast. It's on a little spit of land, of island there, right on the coast, and it's built mostly on soil above permafrost, and the permafrost is thawing, so you have that collapsing soil, and they've actually started to move buildings inland, back over to the mainland, even because of this, because they're potentially gonna lose the whole town at some point. And there's other villages like Kivalina is another one, which is I think on the other side of the bay there, that are losing coastline. So, and these are, one of the main factors again is you have the increased fetch, the waves, especially when you have storms, and the permafrost is thawing, and so you can really lose coastline very quickly. Another aspect that's it kind of relates back to the issues in the last session and concerns in the last session. As we open up the ice cover, we are opening up shipping lanes. Particularly the northern sea route has been largely open, and then the transpolar sea route over the pole is potentially a real shortcut and would be largely through completely international waters. And then there's the Northwest Passage, which still has a lot of issues and will continue because of the thicker ice there in the narrow and shallow channels. But of course, as you are opening up shipping lanes or other resource extraction and things like that, relating to the storms, you have risks there as well. As you put ships into the Arctic and more of them, there's a lot of risk with greater storms, as well as the remaining ice cover. This is a paper recently by Lawrence Mudrick and others at Environment Canada that showed how the change in season is going to increase under different scenarios. So the top line is the 1 degree. That's basically where we're at. And the not ice strengthened is on the left column, and then the 3 on the right are ice strengthened at various strengths. So the weakest to the largest or most strongest, and then the blue shades are the additional strength over what you get from the current not ice strengthened. And you basically see, as you expect, plus 2 degrees, you significantly lengthen the ice season or ice free season, where they can transit or the time they can transit, either through ice-free conditions or lower ice conditions where the less ice strengthened ships can go. The other thing that I mentioned that is an interesting effect as well is the potential for increasing terrestrial snow cover. When you have a big area of open water, you have the cooling atmosphere in the autumn. What happens when you have ocean, warm, moist ocean going across, winds blowing from that onto the cold land, you can get coastal snow. I grew up in Michigan, and that was a very common thing in Michigan and the Midwest. You get the lake effect, what they call the lake effect snow, where the lakes haven't frozen up yet. You get the winds blow from the west or from the south or north, and you get cold air comes across, picks up all the moisture in the heat from the lake, hits the land in that cold air, and it just dumps all snow. So I have sisters actually live right on the coast of Lake Michigan, and you'd be 100 kilometers away and it'd be nice and sunny and clear, and then you get to the coastline and it'd be in the middle of a blizzard, and you get the same effect from the oceans. You can, because again, depending on where the circulation is, you can get going across the open ocean in the autumn over the land, particularly in Siberia as well as in places in Alaska. And we see this is in October. This is from the Rutgers Global Snow Lab, where they're mapping the overall snow extent and anomalies. So this is the anomaly of the total extent in October. And you can actually see there is a pretty clear increasing trend over the last 20 plus years or so, 25 years or so. So this is, in some ways, it might seem counterintuitive. We think of warming, snow should be decreasing. The ice is decreasing, snow is decreasing. It's definitely true that snow is decreasing in the springtime. We're seeing much earlier melt in springtime. But in the autumn, at least in some areas, we're seeing increases, particularly in the Arctic regions. And that is at least partly due to this effect of having this open water source available as the land is cooling and the ocean remains warmer. And November looks very similar to this. I just chose October because it's the most recent data. This is actually on the left is October 2021, and you actually do see 50% or so increased snow cover. That's just 1 month, but the trend on the right shows you that there is a definite increasing trend there. So that's kind of the impacts of the extremes in the Arctic region. Probably not comprehensive, but that's kind of just a quick summary of those. The other extremes that people talk about a lot is the mid-latitude connection, the connection between the Arctic and the changes in the sea ice and the Arctic warming, and how that may affect the mid-latitudes. And this was a really big paper. Jennifer Francis and Steve Vavris in Geophysical Research Letters, published in 2012. And this, in our community, I'd say this made a bang. This was, maybe not quite Einstein special relativity level, but this was a pretty big paper, and really got a lot of attention. And it got a lot of attention in many ways. So the first to kind of just quickly summarize their paper, the idea is you're warming the Arctic and you're losing sea ice. You're warming the Arctic. That's changing the balance between the the cold Arctic and the warmer mid latitudes. And the jet stream kind of is essentially set up by this balance, by the colder Arctic and the warmer mid latitude. And you can break down from time to time as cold air spills out, and the jet stream gets kind of wavy instead of being more west to east flow. And the idea is that as you warm the Arctic, that balance is decreasing. So it's more easy for that outflow of that colder air, which is relatively less cold, to spill out and cause this wavy jet stream. And that does is it weakens the jet stream. You get more of a north-south flow instead of a west to east flow, and that leads to more extreme events. So when you have this wavier jet stream, that allows air from the south to more easily infiltrate north on the one side, or from the south or from the north to infiltrate south. So you can get cold air outbreaks, you can get heat waves. It also tends to slow storm tracks, so you get more extreme events like you can get highs that get stuck, and you get a heat wave and drought. You can get flooding if you get a storm that moves very slowly, as the jet stream doesn't move it out like it normally would. So that's kind of the idea behind that paper, and behind the idea of this connection. And like I said, it got a lot of attention at the time, and it still gets a lot of attention. This is just this last winter. It certainly got a lot of press in the United States, especially when anything happens in Texas, it gets a lot of attention in the United States. But when they had the big cold outbreak, near record low, it was certainly lowest in many, many years, in February 2021, and it caused a big power failure, and people lost power and had pipes breaking and flooding, and I think there are people still recovering from that. So it had a big impact, and it really, it was a cold air outbreak, a very strong cold air outbreak. So, even at this point, there was the connection, or people talked about this, is the warming Arctic, and how that was one thing that could be contributing to that. So, is there actually a connection? So this is where, I think things are pretty, it's been an interesting discussion. There's been a lot of talk. This is my little, I just made a screenshot of my little library of papers I've collected, and this is not even close to being comprehensive. These are just ones I've seen, and I just save them because I think they're kind of interesting. There's like about 25 there in the last 10 years or so, and that, again, this is a pretty small sampling of them. There's a couple I just was looking, I saw in the recent couple days that I haven't even downloaded yet. But it stirred up a lot of talk and a lot of controversy, and particularly from kind of a skeptical community. There were a lot of people that really pushed back and still are pushing back against this, that they don't feel that this connection is really there. That the Francis and Vabris paper looked at some data, some reanalysis data, and basically correlated these changes in the jet stream with the loss of sea ice and with the warming. And of course, we all know correlation does not mean causation. And so a lot of folks, especially tropical climatologists, atmospheric dynamics folks, that really felt that the Arctic is not a big enough player. It's a smaller area. There's not as much energy. That the tropics are really much more of an influence on the mid latitudes compared to the Arctic. So there have been several papers that it wasn't just this this kind of like belief. There was papers that have been published that showed that no, there isn't a link. They don't find a link depending on what data is looked at, and how it's looked at. So it's gone back and forth for many years. This just came out. Well, I shouldn't say just came out. It came out in May, and it made a pretty big splash. And that's one of the things with these kinds of studies. They tend to get a lot of attention in the media. And this one, you can see from the headline here, landmark study cast doubt on controversial theory. So this study basically said, we don't find any link, that it doesn't, the changes in the Arctic don't connect to that. And it got played up quite a bit in the media as like, okay, this is it. This is the answer. This is, we've got it. That there is no link. The headline, and this is in Science, so it's not like this isn't a tabloid New York Post or whatever. So, but the thing that is interesting here is this was a presentation at the European Geophysical Union. This is not a peer-reviewed paper. I assume they're probably going to publish a peer-reviewed paper. I haven't seen it yet, but this is just a small talk at EGU. That's generally research in progress, and yet it's still got a lot of attention. And then but nonetheless, this just came out in September, Judah Cohen's one of the folks that have been pretty big into the research and have found some links between the variability in especially in extreme winters. So this was in September, and saying, yes, there is a link. So it really gets into the weeds. There was a big U.S. National Academies study on this and workshop on this way back in 2013 or 2014, I think it was. That was a big report came out of that. But even since then, I think we're still in this area of, we don't really know. And I think one of the things it's a concern is it may be wishful thinking to some degree. Not to say that like Jennifer Francis and Steve Babris and others that have found links that they're making things up or that they're not interpreting the data correctly. I mean, they're really great scientists. I know Jennifer and Steve, and they do great work, and their papers are good. But I think there are things that depending how you look at the data, it's hard. You can come up with different answers. And one of the things is we're looking at extreme events, and extreme events are by their nature rare. And trying to detect a signal in extreme events and a record that's only about 40 years old is very difficult to do. If you've got something that happens only once in a century and it starts to happen and you've changed things so now it happens once every 50 years, well, do you actually see that in a 40-year record? There are other ways to do kind of attribution and so forth, and people have started to do that. But it's still, I think, too short to really detect it. And again, there's this temptation, I think, in wishful thinking to try to make that connection. And as a scientist, I think we have to always be careful about that. One of the questions, as someone who works in the Arctic, give presentations, especially for sea ice, people in Europe, people in the United States, in the lower 48 United States will say, well, what does this mean for me? And, for Greenland, Antarctica, ice sheet, sea level rise, you can make a connection. For sea ice, it can be hard to do. You can talk about how sea ice is a bellwether. The changes that are happening to sea ice are going to happen to the rest of the globe later. But there's that temptation or desire to really want to say, no, the sea ice loss is going to affect you directly. And so this mid-latitude teleconnection is a great thing to make that connection, to say that big snowstorm you had or that big heat wave, that was due to the sea ice or partly due to the sea ice or the Arctic warming. But it's hard to say if that data is really there yet. But I caveat that also with, you're taking an area roughly the size of Western Europe, the Arctic Ocean, and you're changing it from almost completely ice covered year round to being almost seasonally ice free at least during the summertime. That's changing the albedo from 0.7, 0.8 to 0.1. That's a huge change over a big area. And I just don't think you can make that big of a change without having some effect outside of the Arctic. And I think as the changes continue to occur, and as we get a longer record, I think we will start to see some signal outside of the noise. This has been mentioned many times before. What happens in the Arctic doesn't stay in the Arctic. I do think that is true. So I think I'll end it here. I want to thank Pam Pearson and the International Cryosphere Climate Initiative for inviting me to be here and for the support. Happy to take any questions or open it up to discussion, particularly discussion. Thank you.
So thank you very much, Walt. I want to know, does anyone have any questions online or on the floor? Does anyone have any questions for Walt?
Sorry, I've got a very quick question with regard to the definition for extreme events. How can we define them in a way that would not cause questions and concerns from climate deniers specifically? Because, that's something that they use a lot.
Yeah. Very good question. And I didn't actually define extreme events because, I think in a lot of ways, and like it's talked about in terms of, extreme being something that has a big impact that's rare. You could use statistics. Something that's a 3 sigma event would be an extreme event, for example, or even even higher. So that would be one way to define it, using a base period, storm frequencies or something like that, and looking at the deviation from that. If you start getting, out of beyond 3 sigma, that's something that seems, really rare, that's outside, or even 2 sigma. You could consider 2 sigma is kind of the 95% range. So that would, you'd be in the 5% range. So that's one way of quantifying it. I'm sure people have specific ways of, I know that people have specific ways of doing it, but I didn't define it specifically. But I think that's a good point. Definitely. Yeah.
So thank you very much for the presentation. So you wrote there the data record is still too short. And so my question is, may paleoclimate studies from ice cores can help in bridging this knowledge gap? Thanks.
Yeah, great comment on that. And it definitely, that's the paleoclimate record could certainly help. I'm not a paleoclimate person at all, so I'm not sure what kind of events might get captured in that. Things like coastal flooding and things like that potentially could, I think. But I think, that's a resource that we could certainly look at. And probably people have looked at that. You may be more familiar with that, but I think that's a good point. Yeah.
So I actually have a question, but we've got some more questions. No. So one thing I was just wondering about, just off the back of that question, was the resolution of the data that you've been using to look at these effects. I assume it's fairly coarse resolution to cover the whole of the Arctic, and I was just wondering, as techniques get more and more advanced and we're able to simulate down to higher and higher resolution, maybe pick up some high resolution convection, for example, do you think that the amount of extreme weather events that we pick up and the frequency, do you think it will change in these studies?
Yeah, good question. It certainly could. The reanalysis data that's used for the atmospheric variables is like basically 1 degree, and of course the thing there is that, it's reanalysis is using models and integrating in observations, and in the Arctic, observations tends to be fairly sparse in terms of observations, particularly over the Arctic Ocean. Especially you get anywhere before like 1979 or so. Before there's been buoys since then that fill in some of the Arctic, and there's been more coastal stations. So you have a pretty coarse set of data that's going into that, and you're not going to capture some of these smaller events that can occur. And so I think, if we get to better data, finer data, where we have more data and then finer scale modeling, the models are getting higher resolution. Sea ice models we can get down to 10 kilometers for some models. So that's starting to get some small scale effects, but that's certainly a limitation in terms of our records. Yeah.
I think there's 2 more questions.
Thank you all for a very nice presentation, a highly interesting presentation. Rolf Rønn from AMAP, and your conclusion kind of reached the same as we do in our latest report on the teleconnection chapter. And I think how you ended it here, talking about picking up like an extreme signal by retrospective data is impossible, as you say. But I was wondering, and I would like you just to speculate a bit, like if we kind of agree upon it's very hard to pick up a signal of an extreme event or like a change in extreme events because due to their nature. Would it be any other part of the processes or mechanisms when it comes to this sea ice, air, fluxes of energy and possible talent connections? Are there any mechanisms or processes that are particularly good candidates to look into to try to find this kind of connectedness between Arctic and low latitudes?
Yeah, good question. I'm not probably the best person to answer that because someone like Jennifer Francis would be a really good person to answer this, or others. But the yeah, what they looked at was this, kind of the waviness of the jet stream and how far the jet stream goes north, and one of the things is that you have these rare events happen. Nothing, as far as I would say, not I've seen nothing unprecedented has happened. So it's just a matter of frequency. So that lends the idea that you just need more data. But the physical mechanisms, I think, is the thing that people have been you have warming in the Arctic. That warming starts to go up. It helps spin up the stratosphere. The stratosphere can break down, and then the stratosphere connects with the troposphere, and that's what that may not be a very coherent understanding of the top of my head of the connections there. But so there have been some of these physical mechanisms that have been theorized and looked at with models, and this is where I think it gets interesting and certainly out of beyond kind of my real understanding, at least easy understanding, is you get into the modeling things in this paper. This landmark study did it was a model, and they said, hey, we did it with lower sea ice, with higher sea ice, we didn't see a connection, but does the model have the proper physics to make that connection? Again, I'm not a modeler, so it's hard for me to really evaluate that. Other models, though, other modeling studies have shown, we do it we run it with less sea ice, and we do see increased storms and in China or in Northern Europe. And that's the other thing that I think is difficult about these. You get these extreme events, they happen in different places at different times. So that makes it it's not like, every October storms start becoming more frequent or something like that in Northern Europe. It's like, 1 year you get a really cold outbreak in the Eastern US. The other year it's in Northern Europe. The next year it might be, or 2 years later it's in China, or so it gets really hard. So I think making better physical connection between the actual Arctic warming and the troposphere, the stratosphere, and the connection with the mid latitudes, and getting models that I guess we have more confidence in, or maybe higher resolution, that gets to more fine scale physics that we can compare. I think maybe that's the answer ultimately, to try to do that, along with more data, that we can start to see a signal outside of the noise. So, yeah.
Are there any more questions? Do you have a question?
Thanks. You'll have to indulge me for a second as a complete non-specialist. So just to understand, unpack a little bit. So this paper or this presentation was saying that's not the cause. What is it saying is the cause?
Yeah, good question. I don't remember the specifics right off the top of my head right now, but if I remember correctly, it was the tropics that they saw. I think it was Pacific changes in the Pacific circulation in the North Pacific. I think particularly were the driving mechanisms. Yeah, that's a good point. I mean, if you're going to say this isn't the cause, something else has to be the cause, or should be, right? So they did talk about that. Yeah.
Okay. So I want you to join me in thanking Walt again. Thank you very much.
Okay, thank you.